idea. Some of this stuff is old stuff, some of it is new. So the idea we've got here is this graph to the left shows the velocity of a car carrying a crash dummy, although my numbers are a little too low. This is a slow speed crash issue, actually. This might just be the beginning. But yeah, the reason I said crash dummy car, because if you ever watched them do that on TV, whenever they put usually it's just the frame of the car, and they put it on this like machine that just takes it down a straight path so they can control it really easily. Of course, nobody's driving a crash dummy car. So that would explain why it's a perfectly straight line right here. But this graph gives us the velocity. All right. So for part A, it says, what is the velocity of the car at t equals 3 seconds? So if you look at your graph there, what is the velocity of the car at t equals 3 seconds? We would look right here at 3. Right here, it is 16 feet per second. So since this is the velocity graph, if you're asked about velocity, you're just reading points off of the graph. All right. No calculus involved in that. Okay. But B says, what is the acceleration of the car for the time period shown on the graph? So acceleration is not the point on the graph. All right. If we're looking at velocity, what is acceleration in relation to our velocity? It's the second derivative of your position function. So it's like velocity would be first derivative, acceleration would be second derivative, right? In this case, since we've already got velocity, acceleration is just the derivative of the velocity. And what does the derivative tell us? What? Slope. Slope. So derivative tells you slope. So when I'm asked for the acceleration of this car, I really want to find the slope of that line. And since it's a straight line, it's the same at every point. So if we find slope here, it's a little hard to see. I'm just going to do this. I'm going to use this point right here. This is 0, 7, and then this point was 3, 16. I'm just going to do some slope formula. You could count it if you wanted. So 16 minus 7 over 3 minus 0 is going to give you 9 over 3. So you get 3. What would the units be for this? Feet per second per second. And I'll show you something I think is pretty cool about the units. When we do the slope, we're finding the change in y over the change in x, right? So if we are looking at the change in y over change in x, if I just look at the units for y is on the y-axis, they are feet per second, right? And then the units for the x, that's seconds. All right, so if I wanted to simplify, I could, right there's pretty much feet per second, right? Or if I wanted to simplify it, I could put this over 1, so I'd have feet per second times 1 over second. So sometimes you might write it as feet per second squared. Right. Either one's fine. You can write it like this, feet per second, or you could write feet per second squared. The only reason I like feet per second better is because a lot of times students put the square on the wrong part here. They'll say feet squared per second, which really wouldn't make any sense. Feet squared is area per second, and that wouldn't make any sense when we're talking about the velocity of the car. So, so those units kind of figure themselves out if you just consider what you're doing there. Okay, now I think this is so cool. So if we have this graph of the velocity here, C says how far does the car travel in the first 7 seconds. So we're looking up to right here. Okay, we want to know how far the car traveled. But we don't have anything about its position, right? Any ideas? And I can't even, like, I could say, well, it went 7 feet per second for the first second, so there's 7. But if I do that, it really didn't go 7 feet per second the whole time, right? It went 7 feet per second right at that instant at 0, but by the time you get to the first second, it's already up to 10 feet per second. So it wouldn't really be accurate to say, well, it went 7 for a second, and then it went this far for a second. It wouldn't be that accurate. But what units are so cool. So what we have been doing, we were finding slope, which was changing y over changing x. Okay? So what I want to do is I want to find the area of this area underneath the curve from 0, or the line in this case, from 0 to 7. And let me show you why I want to do that. Okay? So what shape do we have there? What? I heard it. It's a trapezoid. You might need to kind of like turn your head sideways for it to look like a trapezoid to you. But trapezoids have 2 parallel sides and 2 non-parallel sides. So you got opposite sides are parallel. So if I drew it like this, it would be more trapezoid looking to you. But so you could do trapezoid. You also could, of course, just split this into a triangle and a rectangle if you want. But trapezoids are going to make it a little bit quicker for us to do some of these problems. So let's use a trapezoid. So if anybody know the area of a trapezoid? I know it. Okay, it is 1/2 height times base 1 plus base 2. Let me show you one other thing I find really cool. So whenever you have, just to help you remember this, this is sort of a side note, it's not directly related to this problem, but if you had a trapezoid that looks like this, then if you could just make it a square, you could do base times height, right? So if you could like cut off this little piece and put it up here, right? And then maybe cut off this little piece and put it up here, then you just have base times height, and it would be really easy. Well, you can kind of do that by finding the average of these 2 sides right here. So if you were finding the average of those 2 sides, you'd take B1 and B2 and you'd add them together, and then you divide them by 2. Or you might do B1 plus B2 times 1/2. Right? That'd be the average of those 2 bases. And then you would multiply it by the height. That is your trapezoid formula. So that 1/2 B1 plus B2, that's the average of the bases times the height. So that's kind of why that's the trapezoid formula. But you can just memorize this, or I like to think about that. I think it's kind of cool to think of. So if we got trapezoid formula, the height is actually what looks like the width right here, because the height has to be the distance between the 2 parallel sides. So this side right here is actually the height. And then we could call this like our B1, and this side over here our B2. So for this particular case, I'm going to include my units for this. I think the units are so cool. So you got 1/2, and then the height is 7, and that is horizontal, so it is measured in seconds. So 7 seconds. And then B1 plus B2. B1 is 7, and that is vertical, so it's feet per second. Plus the B2, what is that? 28, I think. So 28 feet per second gives us our area of our trapezoid. So I've got 1/2. Actually, I can go ahead and multiply the 1/2 and the 7 together. Let's do that. 3.5 seconds times, if I add 7 and 28, I'm going to get 35 feet per second. So think about what we're doing. Obviously, we're doing 3.5 times 35. With our units, we're doing seconds times feet per second. Alright, so we'll do 3.5 times 35, which is going to give us 122.5. Look what happens here with your units. You've got seconds times feet per second. I can put that second over 1 if I wanted. What's going to happen there with your units? What happens to the seconds? They cancel, and I just get feet, which is how far the car travels. Okay, so what happens if I have a velocity formula and I take the area of the area under that curve, it goes back to the position formula before it. Okay, it is a little bit easier to think of if you're thinking of a straight line. Just think of, let's say you had a constant function here, and if this were hours and this were miles per hour, right? If I find the area of that rectangle, I would have to do base times height, so I'd have to do hours times miles per hour, and then that would be over 1. Hours would cancel. It would give me the number of miles that were traveled if I did that. So by finding that area underneath the curve, we can go back to just position instead of velocity and position there. So this would be, if this were the value here, this is not just the estimate, that would be exactly how far the car traveled, would be 122.5. And so this allows us to go from a derivative, not to the derivative of that, not from velocity to acceleration, but rather going from velocity back to position, which is something we have not been able to do so far. Everything I've given you, typically I gave you the position formula and then asked you about velocity or acceleration, or maybe gave you velocity and asked you about acceleration, but we never started with acceleration and worked our way back for that. So it's kind of cool that this works out. Here's our next one. Okay, this is a similar situation, but this time the graph to the right shows the rate at which the amount of water in a tank changes after 2 minutes. Okay, so this is the rate that the amount of water is changing. All right, I want you guys to look at the first. You can look at all of them if you want, but the first 4 questions, because those are not really new things. Those are things that we can answer based on derivatives that we already know, or maybe not even derivatives. So answer those first 4 questions for me for a second, and then we'll talk about what we've got there. All right, justice for A, at what rate is the amount of water in the tank changing at t equals 3 minutes? The 2 is not right. The 2 would be right if this graph showed us the number of gallons in the tank. But what does this graph show us? The rate of change, so the gallons per minute. So if I want to know the number of gallons per minute, then I just go over here to 3. I go up here. It's at this point right here. And so at 3, the rate of change is just 6 gallons per minute. Oh, sorry. Thanks. So we would just look at 3. You would go over here. It's 6 gallons per minute. It's confusing. And if this were just gallons, then you would be correct. 2 would be the right answer. But it's not. It's gallons per minute. Knowing that, Destiny, at what rate is the amount of water in the tank changing at t equals 6 minutes? Well, what'd you get for part B? Is not 2 for that one. So we're right here, right? 6 minutes is right here. You're going to go over here for the, are you looking at the difference between here and here, maybe? Where'd you get to at the difference? Okay, so you're not looking at the difference. You're just reading it up. Same as part A, you're just reading it off the graph. Okay, so it would just be 8 gallons per minute. So if I ask you about the rate of change of the amount of water in the tank for anything, you just are reading the points off the graph for this. Yes, so make sure what your y-axis is talking about. If we were looking at the change from 3 to 6, it was how much it increased, and 2 would be the answer, but it just wants to know what the rate of change was at that point. Okay. All right, so C is the question that I feel like is terribly confusing. Does the amount of water in the tank ever decrease? Okay, Lily says no. Okay, Lakin says no also. Do some of you think yes? I mean, if you look at this graph, clearly it seems like a yes, right? When you first look at it, it clearly seems like it should be a yes. I would not blame you at all if you said yes. But they are both right. The answer is no. The amount of water in the tank never decreases. It's always increasing. Why? Okay, this is the derivative. This is the rate of change of the amount of water in the tank. So, like at 1 minute, we're increasing it 2 gallons per minute, and then 4 gallons per minute, and then 6 gallons, and then 8 gallons. Even here, whenever it looks like nothing's happening, still your amount of water is increasing at 8 gallons per minute. And then right here, it looks like it's going down. So by the time we get to 10, it looks like we're only at 5, so that's got to be a decrease. It's a decrease in the rate of change, but not in the amount of water. Okay, so for this one, the answer would be no. And your reason would be because the rate of change is always positive. So since you got a positive rate of change, that means water is being added to the tank. For us to see an actual decrease in the amount of water, we would have to see this go down below the x-axis where we had negative rates of change. And that would tell us the amount of water in the tank is decreasing. But the amount of water in the tank is always increasing for this one. Okay, questions on that part? All right, D says, is the rate of change of the amount of water in the tank increasing or decreasing at t equals 5? And actually, it's a little bit of a trick question. It is constant, right? So you would really say neither. Because if we're looking at whether the rate of change is increasing or decreasing, then we are looking at whether or not this line is going up or down. It would be constant right here at 5 minutes, because, or you could think of looking at the slope, and the slope is 0 right here, so the rate of change is not changing. Okay, questions on that? Alright, so if we want to know how much water was added to the tank over the first 10 minutes, then if we want to go from the gallons per minute back to just the number of gallons, right, then we could take gallons per minute and we could multiply it by the minutes, right? So x-axis times y-axis here, and the minutes would cancel, and we would just have gallons, right? Which means that if we find the area of this shape right here, then we can find that amount of water that was added. So what I want you guys to do right now is find that area. Now you could do this a lot of different ways. It does not matter. You can split it up however you would like. You could do this trapezoid and this trapezoid, or you could do, split it this way. However you want. You might do it different ways. You should get the same answer. So I want everybody to find that area for me. Should get 58. And it will be gallons for that. So 58 gallons were added to the tank over this time. Questions? Okay, so sometimes, obviously here this was a math problem that I made up to test your understanding, because probably this is not what really happens as you fill up the tank, right? Now there's definitely, as you fill up the tank, there's definitely some things that could happen where maybe it fills up, more quickly over a little bit of time, and then it's slower and it's constant for a while. That could happen, but probably this might not be the case. So what you're more likely to have is where you have collected some data and you have just certain points, and you don't actually have all of the lines in between. And so let's look at this particular instance. So we've got a drag car travels down a track. Selected speeds of the drag car are given in the table below. So after 0, 0.51, 1.52, and 2.5, we've got the speed of the car. So it starts off at 0, it takes off and races towards the finish line. And of course I've picked the drag car because drag racing, you're going straight. So we could make it much easier than if we circle track racing, more complicated. For A, it says, what is the average acceleration of the car for the 2.5 seconds shown on the table? So average acceleration. Any ideas? Alright, let's use our units to help us on this also. Okay? What are the units for acceleration if we've got seconds and feet per second? What would the acceleration, what would the units be? Feet per second per second. So feet per second per second. Right? So we want to know how many feet per second the car was going every second. When we want to know the average acceleration, so we're not looking at just one single point, we're looking at overall, right? Let's back up just a second. Let's say that I ask you for average. Let's say that you drive from here to Raleigh, and it's 150 miles. And it takes you 2 hours to do that, right? So if I wanted to know your average speed, right, we just take the distance and divide it by the time. The change in your distance divided by the change in the time, right? So for acceleration, if we want average acceleration, we need to know the change in the feet per second over the change in the seconds. And we're going from 0 to 2.5 is what we're looking at here. So we're just really finding the slope between the point 0, 0 and 2.5. 2.5 and 145. Okay, so in that case, it'd be 145 minus 0, and those are both measured in feet per second. And then you would have 2.5 minus 0, and that would be per second. And so 145 over 2.5 should give you 58 again. 58. And that is feet per second, or feet per second squared. So for this particular case, we can't find the actual instantaneous acceleration at a point because we don't have a straight line. On these problems, we had the graph and we could see if we were looking for acceleration for this one, we could just give the slope of the line. But if you have a table, you probably won't be able to do that. So you have to just find the slope between the endpoints, and that'll be the average over that period. Okay. Questions on that? Okay. I just said we couldn't find instantaneous velocity, but B asked us to estimate the acceleration or instantaneous acceleration. But B asked us to estimate the acceleration of the car at 0.75 seconds. So what could we do there? Very good. We're going to use these 2 points right here, right? And we're just going to find the slope between those points. Because the slope of, this is our speed, or we could think of it like velocity if we want. The slope of the speed is going to give you your acceleration. So if we just find slope between these 2 points, we'll do 110 minus 60. And that is feet per second. Both of those are. And then 1 minus 0.5, and that is seconds. So we would get 50 over 0.5, which is going to give us 100 feet per second per second. So it's an estimated slope. It's not exactly that, but it'd be our closest bet. So you'll see like the average acceleration was 58 feet per second squared, but at between 0.5 and 1, it was probably closer to about 100. And so the acceleration, it seems like it's greater at first because you like from here you go 60 feet per second faster, then you only go 50 feet per second faster, then 20, then 10, then 5. If you think about taking off in your car, at first you're getting a lot faster real quick. Maybe not, depending on what you drive. And you're getting a lot faster really quick. But once you get it up past 100, it takes it a while to get a little bit faster. Hopefully you guys don't know about that. You shouldn't do that. But, as you reach your top speed, you can still get a little bit faster, but it's going to take a long time to get a little bit faster for that. We should see if Miss Ball will let us borrow her car for some testing on acceleration rates. The minivan might not produce quite as interesting results, but I bet I can haul a lot more people and stuff than she can. What kind does she have? Yeah. Honestly, like my mom's minivan when I was growing up, it was pretty slow. But my minivan is a lot faster than hers was. It's not that bad. It'll go a little bit. I mean, it's obviously not going to outrun like a sports car, but it's not bad. It's pretty cool, actually. We were talking about it at lunch. I think that Mr. Bashir said that minivans were the fanny packs of cars. So, might be true. But fanny packs are very convenient sometimes. So. And at some point, you don't really care anymore. You just want space for your kids and your stuff. So, it's something that doesn't cost an arm and a leg, because I cannot afford to buy a Denali Suburban or something like that, because those are really expensive. Alright, so for these, those are both talking about derivatives, right? We're talking about slope. But if we're supposed to estimate the distance that the car traveled in the 2.5 seconds, I have already put a table here, a graph here for you, because if all you had was a table, it can be done, and we're going to work our way to being able to do it a little bit better. But it's probably going to make it a little bit easier for us if we try to graph this to figure it out. So if we graph it, we've got at 0, we've got 0, 0.5 is 60, 1 is 110, 1.5 is 30, 2 is 40, and 2.5 is 45. Now, when you think of if you think of a car that speed is increasing, it is going to increase in a smooth fashion in most cases, unless your car has some major issues, some major transmission issues. But so we would have a smooth curve right here, and if we had a smooth curve that curved like this right here, that's probably what we would see. That would be great, but if it's curved, we don't know how to find the area of a shape that's curved like that, right? So since we can't do that, notice this question does ask us to estimate. What I could do is I could pretend like this is a straight line right here, and I could figure out that area, right? And then I could figure out this area right here, and I could figure out this area. It's not going to be perfect, but it'll be pretty close, right? So that's what I want you guys to do. Figure out the area if we put all of those together. I will tell you, this one's definitely easier to do trapezoids for. The first one's obviously a triangle, but the rest of them, they're trapezoids. You put them on there, kind of trapezoids on their side. So try this one here. Okay. If you put two together, like so, maybe from like from like here to here, is that kind of what you're thinking? If you do that, then it cuts this part right here off. So you could do it, yes. What's it going to do to your estimate? It's going to be a little bit worse than if we used the smaller trapezoids, right? So you could do it because it just says estimate, and it would be an estimate, right? But it'll be closer if you do each one separately. If all of our intervals are the same, it goes up by 0.5 each time, right? So notice here that the first number on the table and the last number on the table, they're only there once. All the middle ones are there twice, right? So I could have done 1/2 times 0.5 times 0 plus 2 times 60, 2 times 110, 2 times 130, 2 times 140, and then 145. We're going to see this pattern happening over and over and over again. This is actually what we call the trapezoidal rule. But we will focus on that more specifically later when we get further into this unit, so I won't show you that. But what you just did here was the trapezoidal rule, even though you were really just finding the area of a bunch of trapezoids, right? So, so it's something, there's almost always a question on the AP exam about it, And so you really already know how to do it. I'm going to show you some like shortcut sort of rules, but you already know how to just find that area under the curve. Okay. All right. Last one. This is some actual data. This is happening right now. The table to the right shows the number of daily deaths that have occurred due to the coronavirus since January 23rd, 2020. So I've pulled this off of a website, hopefully that was fairly accurate. It at least looked like to match what I've seen in the news anyway. So these were the deaths per day due to coronavirus. So on February 4th, there were 66 deaths per day. On February 2nd, there were 48, and so forth. So we are going to use this data to answer some questions about what's happening as far as the rates that we see here. So first thing we really need to do is we cannot count this as like 23, 26, 29, 30, 2, 4. We can't do that because we skipped from February, January, and that wouldn't make sense. So let's do this. Let's make January 23rd, let's make that day 0, right? That's when people started realizing, oh no, this is a problem. And we started paying attention, and that's whenever this table had the data on it. So if January 23rd is 0, 26, that'd be 3. This is 0 though. 0, 24 is 1, 25 is 2. Yes, it's 3. Okay. Did I use 3 or did I use 4 when I did this? I put 4. I messed it up. Mine is going to be wrong. Let's see, 29. Let's see, 27 would be 4. 28 would be 5. And 29 would be 6. Would be 7. The 31st would be 8. Then the 1st of February would be 9. The 2nd would be 10. The 3rd would be 11. The 4th would be 12. Now the table that I got this from actually did have every day, but for what we're doing, I didn't want to give you guys every day, so now there could be many things that you might do where maybe you only took data at certain times. Like, for example, it seems like when you look at news stories, flu deaths, it seems like they go by the week on that. Because they'll tell you that there's been 8 more flu deaths due to in this state. But typically that means 8 more in the past week. So they only report those every so often. So it very well could happen. Now, coronavirus, they're really watching really closely. So they probably have, everything timed out very specifically on that right now. But we're looking at the deaths per day here. So it says from January 23rd to January 29th, the number of daily deaths increased at a rate of. So what should we do for this one? Perfect. Okay, so we would do 38 minus 8 over 6 minus 0. So we would have 30 over 6, and we would get 5. And what would our units be? Deaths per day per day. And if you look at it, that's probably about right, because like if you're or close to right, because from this time, so you had 0 the first day, you would have 5 more the next day, you would have 5 more the next day, So the second day you'd have 10. Third day you'd have 15. It was actually a little higher than that. But then you'd have fourth day, fifth day, sixth day. Actually, no, I'm sorry. We should have started at 8. Let's do 8. 8 plus 5. So we know we had 8 the first day. So the second, that's the 0 day. First day would be 13. Second, third. Third is saying 23. It's actually 24. Pretty close, right? And then fourth, fifth, sixth. I guess you're 38. So it's about what is happening, right? But not exactly, because we're just looking at an average right there. Okay. So for B, from January 30th to February 4th, we want to know the rate at which the number of daily deaths is increasing. So, Wendy, what would we do for that one? Good. And so we'll have 66 minus 43 over 12 minus 7. And that will give us 23 over 5, which is going to be 4.6, and that is also deaths per day. That is fine. Yes, if deaths per day squared is fine. So the good news there is while it's still increasing rapidly, at least in this last, the first about a week versus the last about a week, this is increasing slightly less rapidly, although we are still seeing a lot of increase, and that could continue more. So, but slightly good news there. C asks us to estimate the total number of deaths due to the coronavirus between January 23rd and February 4th. So, for this, let me go back so I can see this a little better. All right, so in this case, if we're doing total deaths, this is deaths per day, right? If we took deaths per day and multiplied it by the number of days, then that would just give us the number of total deaths, right? So let's graph these points. Be careful on this. It split it up a little bit weird. So it's like 2.55, 7.510 is how it's counting up right there. Not really ideal. I did this on Desmos and it automatically put those divisions in there. So like 0.8 is just like a little bit above that line right there. And then we would have 324 about right here. And then we would have 638 about right there. 743 right here. 1058 and then 1266 right here. Okay, so if we look at this, it looks pretty linear. Actually, it looks very linear. It's not perfectly linear, but it looks pretty linear. So that we don't all have to do this a bunch of times, let's do this. I'm going to split these into trapezoids like this. And Justice, you find the area of number 1 for me. Destiny, you find the area of number 2. Lakin, find the area of number 3. Liliana, you do 4. And Wendy, you do 5. And you guys are going to be my adder-uppers over here. So you guys find the area of just your trap.